Hey guys, in this video we're going to be looking at Proton NMR. Now I'm going to start the video by talking you through the process, important things that you need to know, and then the bulk of this video is going to be talking you through some example questions, how to interpret this, how to interpret combined techniques with a bit of mass spec and IR in there as well, and then the important things the examiners are looking for. What I want by the end of this video is for you to be pausing the video and racing me through to the answer.
Proton NMR is very similar to carbon NMR, but the big difference is the amount of information we get given in the spectra and how we read it. The number of different sets of peaks that we have shows the number of different environments we're looking at. The chemical shift will show us the type of environment that we're looking at. The integration numbers will show us the relative number or the ratio of hydrogens that are in that environment. And then the spin coupling pattern will show us the adjacent hydrogens. When we're looking at chemical shift, TMS is going to be the standard. This is given the value of 0 and everything else is compared to this. This is tetramethylsilane and it is used because it is symmetrical. So all the protons are in the same environment. The solvent we're looking at could be deuterated chloroform. And deuterium doesn't absorb, so it won't give a peak. Other ones could be deuterated dimethyl sulfoxate. When we're looking at spectra, we are going to have a line across the bottom that's going to show us how far shifted along things are. And this is going to tell us the type of environment that the protons we're looking at are in. For example, if it's between 7 and 8, then chances are it's part of a benzene ring. And if it's all the way over by 11, then chances are it's part of a carboxylic acid. This is all going to be shown on your data sheet. So here we have a very simple hydrocarbon. And if we look at this hydrogen, if we look at this proton, it is in an environment. We can say that proton is attached to a carbon that has 3 hydrogens attached to it. Whereas if we look at this second one, it's got a slightly different proton environment setup. There are 3 different types of environment. The pink protons are all the same. We can describe each of these pink protons as being attached to a carbon that is adjacent to a carbon that has no hydrogens on it. And there are 3 protons that we can describe in this way. So there are 3 protons that are in an identical environment. The purple protons can be described as being attached to a carbon, which is attached to a CH3 group, adjacent to a CH3 group. And there are 2 protons in this environment. The orange ones can be described as being attached to a carbon that is adjacent to a CH2 group. And there are 3 protons in this environment. So for these pink protons, if on a spectra it is adjacent to no hydrogens, then it becomes as a single peak. And because there are 3 protons in this environment, it is going to have an integration number of 3, or be 3 high. The purple ones are adjacent to a CH3 group, which means it will show up as 4 peaks. And because there are 2 protons in this environment, the integration number will be 2. The orange ones are adjacent to a CH2 group. And there are 3 protons in this environment. And then where they are on the spectra is all to do with the chemical shift, the type of environment that they are in. If we want to work out what the split pattern is saying, we need to think about the n+1 rule. The number of peaks in the splitting pattern will be 1 more than the number of hydrogens attached to the adjacent carbon. For example, if there are no hydrogens attached to the adjacent carbon, 0 plus 1 gives us 1, which means we'll have a single peak, which is called a singlet. If it's adjacent to a CH, 1 plus 1 is 2, means we will get 2 peaks, or it will look like a doublet. If it's adjacent to a CH2, 2 plus 1 is 3, we will get 3 peaks, or a triplet. If it's adjacent to a CH3, 3 plus 1 is 4, means we'll get a quartet with 4 peaks. When you do a lot of these, you will start to recognise some patterns and some pairs of patterns that come up frequently. Now, these pairs of patterns may not be directly next to each other. We can have 2 doublets, which means there's going to be a CH group and a CH group. We can have 2 triplets, which means there's going to be a CH2 group and a CH2 group. We can have a triplet and a doublet, meaning we're going to have a CH group and a CH2 group. We can have a quartet and a triplet, showing a CH2 group and a CH3 group. A quartet and a doublet with a CH group and a CH3 group. Or a multiplet, which this one has 7 peaks in it. Now, thinking about our n+1 rule, 7 peaks is going to mean 6 hydrogens, and the most common example of this is going to be 2 CH3 groups or 2 methyl groups attached to the same carbon. Now, when we are looking at peaks, you have to remember that it is next to. So the CH2 group is responsible for the triplet, and the CH3 group is responsible for the quartet. CH2 group responsible for the doublet next to or adjacent to CH3 group responsible for the quartet. So here is our first example question. Predict the NMR splitting that will be shown by 1,3-dioxane. The first thing I'm going to do is just label all of these different positions so we can talk about them clearly. Here is the first place that we have any hydrogens. 4 and 6 are in the same environment, and then 5 is a separate one. The hydrogens at position 2 are going to show a singlet because there are no adjacent hydrogens. 4 and 6 are both next to a CH2 at position 5, so that is going to show as a triplet. And then the pink one is going to show as a quintet. It is next to 4 hydrogens, 2 hydrogens at position 4 and 2 hydrogens at position 6. Using our n+1 rule, that will give us 5 in our splitting pattern. Predict the NMR spectra for methionine. First thing is we're going to identify all of the hydrogens that are going to be in the same type of environment. So there are 3 hydrogens that are the same type here. So the integration number will be 3, or the relative peak height will be 3. And they are next to, or they are adjacent to something that has no hydrogens on it, so it will be a singlet. Moving over to the right, we have 2 more hydrogens that are in the same environment. So our relative peak height is going to be 2. On one side, they're next to no hydrogens, and on the other side, they're next to a CH2. Next to CH2 is going to give us a triplet. Moving right again, we have the purple ones, and it is next to 3 protons. 2 on one side, 1 on the other side, so it's going to be a quartet. We have 1 single proton, which is going to have a relative peak height of 1. It is next to a CH2 group, so it is going to give us a triplet. And then this hydrogen, again, just 1 hydrogen in this environment, so the relative peak height will be 1. And it is attached to something that has no adjacent hydrogen, so it's going to give us a singlet. We can differentiate between the 2 singlets or the 2 triplets based on peak height and chemical shift. And Ester has a mass of 164. Use the NMR spectra to identify this ester. Now you may want to jump straight to the NMR and try and work out what the ester is, but you have to use all of the information in the question to answer it. If you have missed out any bits of information, you are not answering the question fully. So we are going to start by looking at the mass and then working out the formula of this ester. So the ester group, carbon, oxygen, oxygen, is going to have a mass of 44, giving us 120 left over for the rest of the compound. Now your normal way to do this is to take 120 and divide it by 12, and that is going to give you 10. So it could be 10 carbons, but that wouldn't leave us any space for any hydrogens. So if we took that down a little bit to 9 carbons, giving us 108 used up for the carbons, then we would have 12 left over for the hydrogens, giving us a chemical formula of C10, 9 for the rest of the compounds, 1 in the ester, C10H12O2. Now we know what the formula is. Now we can go to the NMR spectra and identify this. And I'm going to take this peak by peak, and this is exactly how I want you to do this in the exam as well. So the first thing we're going to look at is our multiplet. Multiplet tells you it's got lots and lots of things in it. And because of the chemical shift on this over at 7.3, this shows us it is a benzene ring. Once we have a little bit of information, I always like to draw out what we've got so we can start adding together different puzzle pieces. Now we have a triplet. And this is over at 4.4. And looking at our data sheet, this could be due to a CHO or a H2CO. And the triplet tells us that this will be adjacent to a CH2. Again, drawing out the little puzzle pieces. I always like to put spare bonds on so we know what we are looking for. We can make a fairly reasonable assumption that that little extra gap in there is going to be filled by another hydrogen, so it's going to be H2CO. Then we have another triplet. The shift at 2.8 is going to be indicative of a CH2. Then we have our singlet, suggesting to us the rest of the ester functional group. And because we have 3 protons in this environment attached to a carbon that has no protons on it, we can turn that into a CH3 group. Now we can put all these puzzle pieces together and start to draw our complete ester. We can make the fairly logical assumption, because we know it's an ester, that double bonded oxygen attached to the carbon goes to the other oxygen, and that on the end of that is going to go our benzene. And that is our complete ester. 5 different chemicals can have the molecular formula C5H10O2. From the NMR spectra, identify the ester. You may recognise these compounds as being the 5 same compounds we talked about in the carbon NMR video. And in the carbon NMR video, we use that to identify the carboxylic acids. This one, same compounds, we're using it to identify the esters. The first thing we need to do is to work out what all of these compounds could actually be. Then we're going to look at the spectra. There are 3 parts to this spectra, and in your answer you need to refer to every single part. Even if you can work it out after 2 parts, you must refer to every single part in your answer. So looking at this first one, it is a singlet, which means this proton is adjacent to a carbon that doesn't have any hydrogens on it. And the chemical shift shows that it is bonded to an oxygen. So the protons could be adjacent to any of these purple carbons. Now we have our multiplets. Our multiplet is split into 7. So that means we are looking at adjacent 6 hydrogens. The most likely thing for it to be when it is this chemically shifted is 2 CH3 groups. So in this compound and in this compound, we have a CH attached to 2 CH3 groups. And the chemical shift shows that it is also adjacent to a carbon double bonded to an oxygen, giving us the most likely answer of this one here. Now, we have answered this question using only 2 parts of the chemical spectra, but we need to refer to all of them in our answer, so we are going to do the third one. This is a doublet, which means our proton is adjacent to a CH group. Next question. Use the following data to identify the mystery ester. And we have 3 different parts of information here. And for this, we have to refer to every single part of information and make it very clear that we have done that and show the examiner which parts of information we're referring to at which particular time. This can be something as simple as writing a short sentence pointing out which bits of information you've used. We have the percentage mass in this compound of 3 different elements. So the first thing we're going to do is to work out the empirical formula. The empirical formula is C4H8O2, and we know from the question this is an ester, and for it to be an ester we have to have 2 oxygens in there. Looking at our mass spec, we can see our MZ is at 144. So to get our molecular formula, we need to times our empirical formula by 2. Even if you did that just based on the fact that an ester has to have 2 oxygens in it, you must refer to the mass spec data somewhere in your answer. If you do not refer to all of the data given in your answer, you're not going to be accessing the full marks on the mark scheme. So we've done the element by percentage mass, we've done the mass spec, now we just have the NMR to look at. We have a triplet at 1.3 showing us that this, and there are 3 protons in this environment. We have a singlet, which means the proton we're looking at is adjacent to a carbon with no hydrogens attached to it. And there are 9 protons in this environment. The most likely way this would happen is if we had a carbon with 3 methyl groups attached to it. We have another singlet at 2.2, and the chemical shifts on this shows us it's going to be a carbon double bonded to an oxygen. Because it's 2, we can say that there are 2 protons in this environment. Now we can start to add bits together, and the carbon we have with no hydrogens on it is the one that's attached to 3 methyl groups. The last little bit of information we have is that we have a quartet over at 4.2. This is going to show us a HCO, which is going to be adjacent to a CH3 group. And there are 2 protons in this environment. So we can add another one on there, so there are 2 protons in that environment, and there's a CH3 group as well. Now that we've used all the information, we can start to build bits together. We've already added these 2 bits together. So you shouldn't rub things out in an exam, but just for the sake of tidiness, I'm going to rub that bit out because I've used that bit of information. We know this is an ester, so we need to make our ester linkage in there. So we've got CH3 and a CH and a CH3 and a CH2 down here, so we can assume that they are the same. Now we just have 2 halves of a compound, and that looks incredibly messy, so I'm going to draw it out neatly. And there we have our final compound. Identify the mystery compounds. And again, if you haven't got the hint by me saying this enough in this video, you must use all of the information given, and I put this in 4 different colours, all of the information given in the question in your answer, and make it very clear that that is what you have done. So we know the molar mass is 118, and 54.2% of 118 is 63.96. Rounding that, 64 divided by 16 is 4, meaning there are 4 oxygens within this compound. 118 minus 64 gives us 54 left over for the rest of the compound. You can divide 54 by 12, or you can use your 12 times tables. So we can work out there are 4 carbons in this compound. We have 48 used up by the carbons and 64 used up by the oxygens, leaving us 6 left over for the hydrogens, giving us a formula of C4H6O4. So we've used the first 2 bits of information. Now we can use the second bit of information, and to make sure the examiner knows that I'm referring to this, I can simply state the fact that the infrared spectra shows peaks at 1630 to 1820, and another broad peak at 2500 to 3330, showing it's a carboxylic acid. If you just wrote down this is a carboxylic acid without any reference to where you got that information from, you wouldn't be accessing the full marks. It is a very short sentence to make sure the examiner knows we've used the infrared spectra. Now we can look at the NMR. Instead of just saying peak, it is much better to describe the type of peak. So we have a singlet. And the shift of this singlet is indicative of a carboxylic acid group. We have a quartet at 3.4, showing us a carbon-oxygen double bond that is adjacent to a CH3 group from the quartet. And then finally we have a doublet. The shift of this doublet is going to show us carbons attached to R groups, which is going to be adjacent to a CH group. And looking at our chemical formula, we have 4 oxygens in there, and we know it is a carboxylic acid. Now, we don't actually have a large amount of information in here to help us work out the structure of this. But 4 oxygens in a carboxylic acid would suggest a dicarboxylic acid. We know that the hydrogen that is attached to a carbon attached with a bond to an oxygen is also adjacent to a CH3 group. And then because it is a dicarboxylic acid, we can just put the other carboxyl group on the other end. Well done, guys. There are some really tricky questions in this video.
Ouch. Love you too, Prim.